Hello and welcome again to my Physical Science online video lecture supplement series. In today's video, I'm going to be doing a post-quiz review of the Pendulum Lab quiz. So we're looking at the quiz that comes after the Pendulum Lab. So let's go ahead and pull up the Pendulum Lab. And there it is. And let's go ahead and pull up the Pendulum Lab quiz, which is here. So let's go ahead and begin and see what we get. So the first question that it asks, which of these best describes how to make a pendulum? So we've got several options. You can drill a hole in a piece of wood and then heat it. You can pour water on a rope and then freeze it. You can tie a string to a rock, then secure the other end to a hook overhead. You can attach a set of paper clips to each other end to end so that they make a circle. You can drop a ball so it rolls down a ramp, or you can connect a protractor to a compass and then place this next to a bar magnet. So let's go ahead and read what our experimental instructions are to get us started. After looking through the equipment that we need, we could read a summary of the experiment. It says a simple pendulum is a type of harmonic oscillator which consists of a mass bob at the end of a string. The string should have negligible mass compared to the bob, and the mass bob should have negligible length compared to the string. Okay, so it sounds like you need to have a mass at the end of a string. So let's look at these options again. If you drill a hole in a piece of wood and then heat it, there's nothing about having a mass at the end of a string there. Pouring water onto a rope and then freezing it, well, you do have a string in the sense that you've got a rope, but there's no mass at the end of it. This one says you could tie a string to a rock and then secure the other end to a hook overhead. Well, if you tie a string to a rock and then tie the other end to a hook overhead, it sounds like you have a mass bob suspended at the end of a string. So that one must be the right answer. Next thing that it asks, which of the following parameters did you change in this experiment? So let's open that instruction up again. We'll kind of scroll down a little bit. It gives us some details about how to time this. And then here's the actual instructions. And it says, first determine the effects of mass on the pendulum's period. To do this, select a trio of different masses. That is a trio of different weights. The masses should be small and they should vary. So mass is one thing that we're actually varying in this. So let's go ahead and click mass. Is it the only thing that we're varying though? Well, let's look. It says that we should do this for a few different masses. And then as we scroll on a little more, it says now we want to determine the initial angle, whether the initial angle has any effect on the period. And to do this, we will basically test the period at a couple of new angles. So that sounds like we're varying the angle. So let's see if angle is one of the options. There's length, thickness, initial displacement, e.g. pole angle. So that would be this one. Okay, are there any others besides that we do? Well, let's scroll down some more. Then I see an entire table of length and times. And it says basically we need to determine the period versus the pendulum length. Select 9 different initial pendulum string lengths. So that sounds like we're varying the length of the pendulum. So go ahead and pull up in the quiz again. String length is essentially what this length of pendulum thing is. So what about these other things? In all of these cases, you're supposed to just release the pendulum, so you're not varying the speed. It doesn't say anything about changing the string anywhere in here, so you're not changing string thickness. And the only way to really change gravitational acceleration would be either to leave the surface of the planet or get in an elevator, and there's nothing about doing either of those in this experiment. So this one, and this one we just leave alone. So now we go to the next question. If the pendulum makes 10 complete swings in 15 seconds, what is the period of oscillation? So what is the period of oscillation if it goes 10 swings in 15 seconds? Let's pull open the instructions again. And we got to go kind of back up here again. And in this summary, it basically says that you have some reaction time, and that's something you did in the first lab. And so you're trying to minimize the effect of this reaction time. And then it basically says it's advantageous to time over several full oscillations, at least 10 seconds worth, and divide this time by the number of oscillations. So if you time 10 oscillations and it takes 12 seconds, then the period is 12 seconds divided by 10. If 10 oscillations only takes 3 seconds, then the period is 3 seconds divided by 10. Okay, just from that example alone, you can see that there's a pattern here. And the pattern is take the time and divide by the number of oscillations that happen in that amount of time, and you get the period. So let's see what it says on this thing. It says you have 10 complete swings in 15 seconds. So we need to divide this time, 15 seconds, by this number of swings, 10. So you can easily divide anything by 10. Basically, that means move the decimal place over by 1. So in this case, it's 15 seconds over 10. That's 1.5 seconds. So you'd put in a 1.5 here. Okay, now question number 4. If you increase the mass of the pendulum bob, what happens to the pendulum's period of oscillation? Okay, you have to actually do the experiment here to see what happens when you increase these different parameters. There is, however, a bit of a hint implied in these instructions. Namely, you don't do a whole lot of changes to the mass. Usually, if something is supposed to change the period, then we would do more measurements with that something. Then there's this question about, do the periods differ substantially from each other? If the periods all look like they are close together, then this means the mass does not have a significant effect on the period. So those should be strongly hinting that the answer here is no effect. And if you do this experiment and you do it carefully enough, you'll notice that when you change the mass, that's increase or decrease, the period of the pendulum should stay the same. Notice that the mass was changed, so you shouldn't be selecting this option. If you increase the initial displacement, what happens? Well, it's basically the same thing here. It gives you this strong suggestion that maybe they should be the same. If you actually do this experiment, you'll find that the pole angle does not have an appreciable effect on the period, in particular if you are at a small pole angle. I should add at this point that that's kind of important for this experiment, because after each swing that the pendulum makes, the maximum angle that it's going to reach gets a little bit smaller. This is due to stuff like drag from the air, maybe a little bit of friction between the pendulum string and the suspension point, etc. So each swing gets a little bit smaller. You may not notice that it's getting smaller, but if you let it swing back and forth for a very long amount of time, you'll notice eventually that it's sort of getting smaller and smaller and eventually stops. That's why, for example, you have to wind up a old grandfather clock every so often. So if the angle has some effect on the period, that means, among other things, that with a grandfather clock, as the clock begins winding down, then the period of the oscillation should be either getting longer or getting shorter. And that means that the seconds that are being tracked by that clock should either get longer or shorter. So it should either lose time or gain time as a result. And you know that that doesn't happen, not appreciably anyway. Furthermore, if this happened and you were told you have to time for so many swings and then divide by the number of swings, well, this process wouldn't work very well. You'd be getting an average period, but the average period doesn't necessarily correspond to the period for your initial pull angle unless each swing has the same period. So it turns out that the angle does not have an effect that you can measure for a small angle on the period. So we can say stays the same. Okay, then we're asked that if you increase the length of the pendulum, what's going to happen to the pendulum's period of oscillation? So again, you should have collected some data in which you change the length and time for as many oscillations as you need to, more than 10 or 10 or more. I did actually 20 when I gave you this sample piece, but you can basically attempt 10 or 15 or however many you feel like you need. And so you should be filling out this table, or you could do it in a spreadsheet. So I'm going to go ahead and open up the Excel spreadsheet, which is like this. Basically, I have some data that I also took for mass versus period and for angle versus period. I did for more of both than I needed to. And you can actually see that the mass versus period on average isn't changing very much. The angle versus period on average is not changing very much. These are under these conditions. The length, unless otherwise specified, is 1 meter. The mass, unless otherwise specified, is a kilogram. The angle, unless otherwise specified, is 10 degrees. So if you were to plot these things, you would in both cases get a horizontal line of if you put this on the x-axis and this on the y-axis. So let's turn to the length versus period. And you can see that as I increase the length, the period also appears to be increasing, and hence also the period squared is increasing. So these numbers are getting bigger as I go down, just as these numbers are getting bigger as I go down. So the answer, therefore, is that as you increase the length, the period also is going to increase. Okay, the next question says that if you increase the number of oscillations for which you time, what will happen to the pendulum's period of oscillation? The implicit assumption so far in this discussion has been that you can time for as many oscillations as you want or need, and that you won't affect the period. That is what this entire summary about timing over many oscillations to reduce the impact of your reaction time is. In fact, if you read on in this paragraph, it states rather explicitly that this works because the period of oscillation is not dependent on the number of oscillations during which you observe the pendulum. So the answer, in other words, to this is if you increase the number of oscillations, then the period should stay the same. Question 8 then asks, which of the following does the period of the pendulum actually depend upon? Well, that's kind of the same question as questions 4, 5, and 6. It's just basically asking you to pick which one of these things has some real effect on the pendulum. And we found that the mass and therefore the weight didn't matter, and that the initial pull angle doesn't matter, but that the length of the string does. So that brings us on to question 9. And it asks, what axis do you end up squaring to make a linear graph? Well, that may seem like a weird question. Remember that you're supposed to have made a graph in this, so it might be worth asking, what should you have on the two axes of the graph? So I'll go ahead and pull open the spreadsheet again. Basically, your graph should end up looking like a plot of the period on the y-axis versus the length on the x-axis. So that's the first thing that you should be plotting according to these directions. Let's go ahead and add a graph to this data that we have for length versus period, since we're supposed to do that according to the directions. The way that we're going to do that is in Excel, you'd go to Insert, and then you go over to Charts, and you select a scatter chart. Then I am right-clicking on this thing and going to Select Data. I add a data series. I click on Select the X values. The length should be what's on the x-axis. Then I select the y values, so it should be period on the y-axis. And I end up getting a graph that basically looks like this. And so this is basically a period versus length for a pendulum graph. So that is the graph that I have from this data. And of course I have a bit more data on here than I asked you to take. In fact, if you pick even increment sizes of 0.25, you'd basically have only this part of the data, which sort of is from this dot onward, or really from this dot onward. So I have more data points than I asked you to get, but it's just to really highlight that this is not a line. You can see that it is in fact curving. So you are going to have to square an axis. So how do you do that? Well, let's go ahead and add another graph to this. And we're going to basically repeat what we've done before. But this time I'm going to, instead of putting period on the y-axis, I'm going to again put the length on the x-axis, and on the y-axis I'm going to go with the period squared column. That's a column that you're supposed to make in your lab. So if you look at the lab, what it tells you to make, in this data table you have length, time, period, which is this time divided by the number of oscillations, and then you have period squared. So I've basically just made that additional column here. In fact, you can see that I've used a formula equals E29. That would be this one squared. This one right here was the time divided by the number of oscillations. So now we look at this, and this looks a lot more like a line. You can see that it not only is a line, but also is a line that you could, for example, add a trend line to or whatever. So what axis did I square? Well, I squared the period axis in length versus period. So let's go back to that quiz. And what axis did you square? Period axis in period versus length. So is that one of these options? Well, you have period axis in period versus mass. Well, this is the wrong graph. Period axis in period versus length. There it is. So, and I didn't need to do any of these other ones, so it must be that. So then I come down here, and question 10 is starting to look a little more odd. It basically says, which of these is a likely equation relating period to the other parameters in the pendulum? Now, before I go and select one, let's just come back here and look at what this graph looks like. This graph makes a line. All lines have the same basic equation. Any line that you make, if you have something like this, and you have a line that you are able to graph out of this, like so, here is your y-axis, here is your x-axis. The equation that goes with this line is always going to be y equals mx plus b. This is y equals slope times x plus y-intercept. Now, what are these y and x's? Well, you look at whatever is actually on your y-axis and your x-axis. So for your actual graph, the one that you actually made, this one right here is period squared. This one right here was length. So the equation that you have at this point, and by the way, if you look on the actual line that I made, this right here actually goes through the point 0, 0. So that means that the y-intercept is 0. So this one has an equation of the form period squared equals slope, which if it is a line, then the slope is constant. So it is some constant times length. So we need some formula of that form. And by the way, the shorthand of this would be something like t squared is equal to c times L. That is the shorthand version of this. So let's go back to that question and see what our options are. You have period equals some proportionality constant times mass. Nope. Period equals some proportionality constant times length. Close, but not quite right. Because we only have period to the 1 power here. You need period squared. Period equals some constant times the angle. Nope. You can eliminate these ones that have angle or mass in them because we established that angle and mass don't affect period. So basically we're looking for something that has a period in it and a length in it. It should be a period squared and a length to the first. So this one's out, this one's out, this one's out. Here we go. Period squared equals constant times length. Period squared equals some constant times length. So we select this one. Also, I'm sorry for this weird spacing on these. I don't know why it has done that. I did not put this kind of strange spacing between options. Hopefully this isn't too confusing. Okay, the last question on here is what are the units of the proportionality constant above? So we're looking for the units that go with C. Well, coming back to this little workspace, the units should be the units of slope. So C is equal to slope, and that's equal to rise over run. So for our graph, the rise is always the vertical change. That would be a period squared. So that's period, which is in seconds, and that is squared, divided by run. So that's a length, and length is in meters. So the units here have to be seconds squared per meter, which is actually the exact opposite of the units that you'd get, or the reciprocal of the units that you'd get if you were looking for an acceleration. Remember, acceleration is meters per second squared. So we have seconds squared per meter here. So let's see, is that an option here? We have meters per kilogram. No, we don't need kilograms. We have seconds per kilogram. Same comment. Seconds per meter. Well, that's not the same thing as seconds squared per meter, so no. Meters squared per kilogram. No, we don't need kilograms. Seconds squared per kilogram. No, we don't need that. So the answer must be none of these. So now we have the answers to everything on this quiz. So we should be able at this point to submit. So submission complete, and we open this thing up. Temp score 115 out of 100, and if we look through here, it's 10 out of 10. So everything on here is therefore correct. So that is the answers to everything that was on this quiz. There are additional questions that could have been asked, but that I did not, in fact, ask on this particular quiz. For example, if you look back here in the handout, it suggests that the gravitational acceleration is 9.8, and that should show up in one or another of your graphs. I suggested now in this video exactly where that should show up, namely the slope of that period squared versus time graph, versus a length graph, this one right here. That slope had units of seconds squared versus seconds squared per meter, and that would be the inverse, or the reciprocal, I should say, of the units that we had for an acceleration. So that's basically the inverse of the units for g, because g is just a type of acceleration. And basically what that suggests is that the slope must be related to the free fall acceleration somehow. It turns out that the slope is related to the free fall acceleration somehow. In fact, the slope is going to be given by this. It's actually going to be slope equals 4 pi squared over g. Here's your free fall acceleration. I'm not going to belabor this point of where does the 4 pi squared come from. That is something that can be derived and would be in a slightly more advanced physics class, like the general physics class kind of sort of dances around it a little bit. The introductory physics with calculus class actually does do this derivation. That's the class that the freshmen in the physics major and maybe the sophomores in the chemistry major end up taking. But it involves a little bit more math than what I would want to have you guys do in physical science. It's basically like a simple differential equation, sort of some calculus is involved. So I'm going to close on that thought. I hope that you guys found this video helpful, and thanks for watching.